Hello, my name is Hearne, and this is my Excel report. Uh, I have my contact details here. If for any reason anybody watching this ever needs to contact me, feel free to use this phone number or either one of these email addresses. Um, my major is social work, and I'll talk a little more about that later. So let's go ahead and get into this report. The first scenario we're going to be looking at is the relativity and number density scenario. So in this scenario, the first thing that we did was checked out that really cool Scale of the Universe app that shows you all the different examples of sizes of things throughout the universe, going all the way down into subatomic particles like quarks and strings, and then all the way up to all of the different bodies of the universe. I picked out just three quick examples here. The smallest one that I picked out was a water molecule. I picked it because water is incredibly important for life, and I thought it was pretty interesting to see how water related to everything else. So as you can see here, water is 280 picometers across, or water molecule is 280 picometers across, which is 10.8 times 10 to the negative 10th meters across, which is pretty small. And then going up a bit, up to a blue whale, which is one of my favorite animals, which is why I picked it. A blue whale is 30 meters, so that would be 3 times 10 to the first. It's also the largest animal to have ever existed, which is pretty interesting that the largest animal to ever exist is currently alive today. And then getting up into astronomical bodies, I use the Pillars of Creation as an example because I've always loved the Pillars of Creation. They have a super cool story. They are about 10 light years across, which is 1 times 10 to the 17th meters. So they're quite big. They are also 7,000 light years away from us, which means it takes light 7,000 years to travel from where the Pillars of Creation are in space to us on Earth to be able to view it. So what we're actually looking at when we see the Pillars of Creation in the sky, on the rare occasion that we can, is light that's 7,000 years old. And the current theory is that the Pillars of Creation were actually destroyed by a supernova 6,000 years ago. And if that is true, then that means in 1,000 years, people on Earth will be able to observe the destruction of the Pillars of Creation. And eventually, if that theory is true, we will no longer be able to see the Pillars of Creation, which I thought was very fitting and quite interesting. So those are just examples of how relatively different sizes are of various things in the universe. The next thing that we did in the module was we took the ones that we chose, these objects that we chose, and threw them up in a nice looking chart, which I have done here. You can see there are the 3 items that I chose, their size in standard notation, and then their size in scientific notation, which is much prettier to look at. Then after that, we got more into comparing the relativistic nature of speed, specifically with different astronomical bodies, to try to figure out how fast we're really moving at one time. For instance, right now, from my perspective, I'm not moving at all. I'm sitting down at my desk. But when you take into consideration that the Earth is rotating at roughly 1,000 miles per hour, then I'm actually moving 1,000 miles per hour relative to the rest of the surface of the Earth because we're rotating around. But the Earth isn't just rotating around in one fixed place. The Earth itself is rotating on its axis, and it's also orbiting at the same time that it's rotating around the sun. And it's orbiting around the sun at 67,000 miles per hour, 6.7 times 10 to the fourth. But not only is the Earth moving around the sun, our entire solar system is moving relative to the rest of the galaxy, and the rest of the solar systems within that galaxy. So you can see here our solar system relative to the rest of the galaxy is moving at 1,302,500 miles per hour. And not only that, the Andromeda galaxy, which is the galaxy that is the closest galaxy to us, is also moving at 250,000 miles per hour. And the Milky Way is orbiting at 1,300,000 miles per hour. And then our local group, meaning the local observable space around us, is also moving at 4,586,000 miles per hour. So if we take in all of these different speeds that we are moving relative to, even just standing still, or in my case, sitting still, we are actually moving at roughly 7,506,537 miles per hour, which is pretty crazy to think about. Now you can see we broke it up into a little chart so it would be easier to stare at instead of just staring at a table of numbers. So this is breaking down the body movements relative to life on Earth and how fast each one of those is compared to our total speed. So you can see Earth, the rotation speed of Earth barely factors in. It's only here at 0%. The speed of Earth orbiting around the sun factors in a little more. It's at 1%. The Andromeda galaxy speed factors in a little more than that at 3%. Then the next is the speed of the Milky Way orbiting, which takes up 17% of that overall 7.5 million. Then our solar system moving takes up an 18% of that. But over here, we can see that the local group speed is taking up a massive 61% of that 7.5 million, which makes sense because the local group speed is 4.5, almost 4.6 million. And this is just a different representation of the same thing, but instead of it being percentages of that total number, it's showing exactly what those numbers are in a 3D bar graph. So you can see just like up here where the Earth's rotation, Earth orbit, and Andromeda galaxy speed were barely a factor, we can see they're so barely a factor that these two, you can't even see them raised. The Andromeda galaxy, you can see raised a tiny little bit. You can see the solar system raised and the Milky Way orbit raised a little more. They're roughly the same, which makes sense because they should be. The Milky Way orbit takes up 17% of that number. The solar system takes up 18% of that number. And then all the way on the end here, we have the massive, massive local group speed, which is taking up the 61% of the total relative speed for life on Earth. And that's all we really did on this first scenario. We were just kind of getting introduced to making these charts and graphs and tables. And we're going to get more into that in our second scenario, which is about misleading data. Now, popping back over to the first scenario just real quick, you can see here that all of our data, especially in these two tables, has been represented fairly. The y-axis here starts at 0 and it increases a fair amount each time. It's a consistent amount and it starts at 0 like you would expect. That's why we see such massive differences between these numbers. If we, for instance, started this y-axis at say 1.3 million, because these two numbers here are right there at 1.3 million, instead of it being clear that the Earth's rotation and Earth orbit and Andromeda galaxy speed were far smaller than these two numbers, if we started the y-axis off at 1.3 million, then all 5 of these would be as small as this Earth rotation here, which wouldn't be fairly representing the data, because it would make it look like these different entries in the table, or in this graph rather, are much closer together than they actually are. So it's very important to be able to understand when data is being misleading, and be able to understand or be able to represent your own data fairly, so that you don't mislead other people, either intentionally or unintentionally. So as a fantastic example of this, we took the unemployment rate percentages for the years that Bill Clinton was in office, and for the years that George Bush was in office. And you can see in the table here, there's barely a difference between them. This is actually the difference right here. There's 0.02% difference between their unemployment rates. That is tiny. But in the original graph that we were studying, the y-axis was represented in a very unfair manner, because here there looks like there's a pretty big difference between them. That definitely makes you think that Clinton has, I mean, to my eyes, that bar looks about 3 times as big as Bush's bar. So that makes people believe that Clinton's unemployment rate was 3 times bigger than Bush's, which is not true. I mean, that is such a negligible difference. There's essentially no difference between their unemployment rates. But because they didn't start their y-axis at 0, they started it at just under where the Bush rate starts, and they increase it by such a small amount each time, it makes that very small difference look much bigger than it actually is. And that's what can happen if you don't pay very close attention to how people are giving you info, how they're representing the info that they're giving to you. Because if you didn't look at the y-axis here, you could very easily believe that Clinton's unemployment rate was 3 times bigger than Bush's, when in actuality, it's barely bigger at all. And sometimes, this graph is nice and easy to understand because it's a very sparse graph, but sometimes graphs can even make their axis titles or the labels on the axes lines here very hard to read, making the data even more misleading. So we can see over here that I've created a table, or I've created a bar graph that is fairly representing the percentages. And as you can see, I mean, with my eyes, I can't see a difference between these two, because we know that the difference really only is 0.02. And we have a couple more examples of this same thing. So this is average bowling scores with Diana, Hilda, and Emily here. In the unfairly represented version of the graph, it looks like Emily is a much better bowler than the other two, and it looks like Hilda is the worst bowler. And although that is true that Emily is the best bowler and Hilda is the worst, it's nowhere near as much of a difference as it appears with this first graph. And you can see here on the second graph that has been represented fairly, that they are quite close together. There is still a difference. Like you can see, Emily's a little higher than these two, and Hilda's a little lower than these two, but it's much, much closer to what it actually is. And here is our third example. This is a good example because, unlike these, which are quite sparse graphs, this has been touched up with a little bit of graphic design, and it's also not labeled super well. So this is even more misleading, because as you can see here, whoever created this graph, this pie chart here, wants people to believe that the city has only contributed, that looks about half, maybe even a little under half there, wants to make you believe that the city has only contributed half of the total funding for this arena. When in actuality, if you look at the numbers here or at our corrected pie chart, the city is contributing about 65%. And this unknown company is only committing 2%, but here it looks like maybe 10 to 15%. It's much bigger than it should be. Maloof's is, that one is actually about right. That looks to be about 21%-ish, maybe, of the graph at 85 million. AEG is definitely taking up too much room, though. They only contributed 50 million, which was 12% of the total area, and they look about the same as Maloof's, which contributed 21%. They also look just a little bigger than this unknown contributors here, who only contributed 2% to the entire project. So that is a really good example of how data, and especially graphic charts and infographics, can be extremely misleading if you don't pay close attention and think critically by yourself, independently of whatever information is being presented to you. Then we have one more example here. This is a slightly unorthodox pie chart. You can see all the rest of these are being represented in a fairly typical manner. And if you look at our corrected pie chart, it looks like they're taking up about the amount of space that they should be, right? Because ACC PAS here is accounting for 23% of, or sorry, 24% of the percentage of sales, and over here it looks like, yeah, that's about 24%. I mean, it's a little bigger than it should be here, but it's much closer. However, the really unusual thing is this middle circle here. Instead of being another slice of the pie, Cartera is being represented as a circle inside this pie graph. The problem is they're only contributing 4.5% to the total sales numbers, but this part of the graph is taking up more than 4.5% of the graph. It's actually taking up 13.7% of the graph. So this blue circle here is a rough estimate. You can see if I move it over here, it is roughly the same size as the total chart. And this yellow circle is a rough estimate of how big the Cartera segment of this chart is taking up. So if we align them, this should be pretty close to how much area of the chart the Cartera section is taking up. So we found the area of this blue circle, and the way that you can do that is if you select the circle, so there's this box around it, and you go to format. Let me see if I can, hold on, excuse me, just one second. Okay, sorry about that interruption. I had to answer a phone call. So if, like I was saying, if you select your blue circle and you right click on it, sometimes it's a little finicky. If you get the one that just has 3 options, try moving your cursor around until you get this long list, and you click on Format Shape here. And if you go over to the Size and Properties tab, which looks like this, and you open up the size, you'll be able to see the area of it. So we took the area of the circle because the formula to find the area of a circle is pi, which we have up here, pi times the radius of the circle squared. So if you go back to that format shape like I was talking about, you go to size, this width here is how wide the circle is. Now, if this was a perfect circle, the width and the height should be the same. We're only doing a rough estimate, so it's all right that it's not exactly the same. But in a perfect circle, the width and the height would be the same because a circle's diameter is the same all the way around the circle. No matter which section you take, the diameter will never change. So we're going to use this 2.7 number here as the diameter of our circle. But the formula needs a radius, not the diameter. And a radius is from the center of a circle to the edge of the circle. So in order to find the radius, all we have to do is take half of the diameter. So you can see up here on our formula bar that we put our diameter in here. We took half of it. We squared that number that we would get, and then we multiplied that by pi, which gave us an area of 5.72 units. There's not units specified here because this isn't a real world measurement we're doing. We do the same process for this yellow circle. As you can see, the radius of this yellow circle was 1. So we took half of 1, which is a half, and we squared that and we multiplied it by pi, and we got an area of 0.78 units. And then we multiplied this cell, or sorry, we divided this cell by this cell to find out the percentage of area that this yellow circle is taking up of the blue circle. And it turns out that this yellow circle is taking up about 13.7% of the blue circle, which means that Cartera is taking up much more area than they should be, about 9% more area than they should be. So in our corrected graph, you can see when they're taking up the proper amount of area, they are much smaller than they were before. And I believe that we have covered everything here. The last thing that I want to talk about here is why it's important to be able to both interpret when data has been misrepresented and to be able to present data in a fair and accurate way. So this example here is an excellent one to talk about why it's important to understand how to analyze data yourself and to know when data is being manipulated. Actually, this example is even better because this can happen in politics a lot. It can happen in anything where someone has a vested interest in making people believe something that may not necessarily be true. So in this example, whoever created this original graph clearly wanted people to believe that Clinton had a far greater unemployment rate than Bush did, which is not true. It is greater, but not far greater. It's only 0.02% greater. So whoever created this original graph wanted to manipulate people into believing something that wasn't true. And to do that, they used data. And they used a way of manipulating data to represent it in a very unfair way. And it's very important for people, especially everyday people like us. We don't have as much power as the people who are being talked about here, or probably even the person who originally created this graph. There's a lot of things that we just have to take people's word for, or we can't know fully for ourselves. So in any area where we can independently verify things, we should independently verify things because it is a great advantage to be able to make sure that all the information being presented to us is fair and that we understand fully for ourselves as much as we possibly can. And on the other side of the coin, it's also invaluable to be able to present data in a fair and easy to understand way. Because presuming that you are not intentionally trying to mislead people, take for example this bowling averages. That's a pretty innocent thing. Whoever created an original graph looking like this may not have necessarily been intentionally trying to make people believe that Emily was a much better bowler than these other two. They may just have made a mistake and had a range that was a little too small and they didn't start at 0 like they should have. And instead of their data being represented in this nice, fair, and easy to understand way, they accidentally created something like this. And there's so many different ways that that could go wrong, both in education or in any career force. Representing yourself or your data or your findings or your words in an unfair or misleading way is always dangerous. So now that we've talked about how to understand and present data, let's move on to populations and probabilities within those populations. So this scenario is dealing with the percentage and the number of Americans who have obesity, type 2 diabetes, and high blood pressure, and any combination of those people. So you can see up here, at the time that I created this report, the population of America was 329.6 million. By the time I'm creating this video, that number will have most certainly gone up. But at the time of creating, it was 329.6 million. So if you look over here at our Venn diagram, this number up here is our universe, which means that any numbers from this total that aren't represented in one of these sections of the Venn diagram must be here. So you can see we have 208.1 million Americans who don't have any of the 3 of these diseases, either obesity, type 2 diabetes, or high blood pressure. So 208.1 million is 63.1% of Americans don't have any of those. That means that a little over a third of Americans do have at least one of these diseases. And as you can see, if we go to obesity, we have 10.3 million, we have 10.3 million Americans who have obesity, but they do not have type 2 diabetes or high blood pressure. Because if they had type 2 diabetes and obesity, they would be in this section here. If they had type 2 diabetes, if they had obesity and high blood pressure, they would be in this section here. And if they had all 3, they would be in this section here. So we have 10.3 million Americans have obesity, but not type 2 diabetes or high blood pressure, which if we just take a look over here at our chart, is 3.1% of Americans. Oh, I don't need to do that because I have this nice handy Venn diagram right below me that gives me all that same information. So we can see that all of these different sections have different percentages or numbers associated with them. And if we go down here to the percentage, you can see it's actually more likely that somebody would have all 3 diseases than it is to have any one of these diseases individually, right? Because the percentage chance for someone to have only type 2 diabetes and not one of these other 2 is only 0.1%. The percentage for obesity is 3.1, and the percentage for high blood pressure is 6.8. But the percentage to have all 3 of them, your percentage chance is 8.5 on average. And you can see the percentage chance to have obesity and high blood pressure is 16.4%. And the percentage chance for these other 2 sections are lower than the other ones, but still bigger than the percentage chance to have type 2 diabetes. So if we go up here, this chart here, this whole chart is what was used to create these Venn diagrams on the left here. We have over here the raw numbers. So we have 329.6 million Americans total. 95.6 of them had obesity. 34.6 million, 95.6 million of them had obesity. 34.6 million of them had type 2 diabetes. 107.8 million of them had high blood pressure. So you can see that is a, you can see 32.7% had high blood pressure, 29.0% had obesity, and 10.5% had type 2 diabetes. And if we add those three numbers up, then that should be 37.9%. Not yet, because see, I almost made a mistake there, because we're not done talking about this data, because if we add all these three things up, you will notice that they will add up to greater than the 37.9% missing from this number here. That's because some of these Venn diagram sections overlap. For instance, this is just saying 95.6 million people have obesity. That's not saying that 95.6 million people only have obesity. To find that, we would need to take the total number of people that have obesity and subtract the number of people who had obesity and type 2 diabetes, subtract the number of people that had obesity and high blood pressure, and subtract the number of people who had all three diseases. And once we do that, we find that there's only 10.3 million people who only have obesity. And you can see that is what's represented over here. So the left side of this table is the raw numbers, and then we use those to be able to factor out all the people who are representing multiple spots in the Venn diagram, to make sure that each person is only put into one section, because you can't have one person be in multiple sections, or it wouldn't be represented fairly and you would be misleading people with your data. Down here, we have a map of the obesity rate across the US from state to state. Colorado is number one. Let's see, I wrote up here how much Colorado's. So Colorado has an obesity rate of 23.0%. You can see right there. And that was taken from this source. So they are number one in the nation. They have the lowest obesity rate in the nation at 23%, which is still pretty high. That means that if you took a random person off the street of Colorado, they would have a 23% chance of having obesity. But that's nowhere near as high as Arkansas's, which actually has the third highest obesity rate as of 2018 in the country, which is 37.1%. So that means that in Arkansas, there's a 37.1% chance that a random person would have obesity. Now, at first, that might seem a little strange that there might be such a big difference between states in the same country, and they're not even all that far apart. You know, we're here in Arkansas. Colorado is not that far away, but we're worlds away in terms of obesity rates. But there's a lot of different things that can factor in to, oh, what have I done? Had a little Excel snafu. There's a number of things that can factor in to such a big difference in obesity rates. For instance, Colorado, these numbers were last taken of 2009. Unfortunately, there aren't more current numbers for these, but we can imagine they probably would keep to about the same trend. So in 2009, Colorado spent $31 billion on healthcare, when Arkansas only spent $17.8 billion on healthcare. So that is not quite double, but it's almost double it's almost double the amount of money that Colorado spent on healthcare versus Arkansas. So if a state is spending that much more money on their healthcare, it makes sense that they would probably have lower rates of obesity. And I would predict that if we compared Colorado's rates of diseases for other things besides just obesity, type 2 diabetes, or this is actually just comparing obesity, but I would suspect that if we compared Colorado and Arkansas, that Colorado would probably have a lower rate of many forms of diseases compared to Arkansas, because they spend almost double as much money on Arkansas in healthcare than Arkansas does every year. The next scenario that we're going to be looking at, because I believe that we have covered everything here, is the measures of center and distributions. So that's a big, long, fancy way of basically talking about how data is normalized throughout a set. So the measures of center are these numbers here. These numbers or these terms are collectively called the measures of center. So a range is the difference between the greatest data set and the smallest. I'm actually using an older version of this document here, which doesn't have the range in it. So we're going to calculate the range live here. So to calculate the range live, we're going to put an equal sign in there. We want to take the biggest data entry in our table. So for this table, this is looking at a randomly selected group of Army recruits' BMIs. So the greatest BMI was 21.4. So after we hit the equal sign, we're going to click on that cell. And then we are going to subtract the smallest data set, the data entry from this set, and hit enter. And we can see that the range of this data set is 2.9. So all those numbers are pretty closely packed together. If we go over here and we do the same thing here that we did in the other data set, you will see that this range over here is much bigger. It's 19.3, the difference between the largest entry and the smallest entry. Oh, sorry, I messed up on this because this hasn't been arranged in numerical order yet. So actually the largest entry here is that 25.7. Sometimes mistakes happen, that's all right. So 25.7, and the smallest entry is this 14.1. That's a good working example of why you should always check your own work, because if I had not checked my work there, I would have allowed a mistake to remain there. So the biggest data entry that we have in this table is actually 72.5, and the smallest one is actually 16.8. So you can see the ranges are bigger than they were before, but the same trend remains true. The Army recruits BMI range is significantly smaller than the random mall shoppers BMI range, which is at 55.7. So the range is the difference between the smallest number and the largest number. The median is the number that is in the middle of the data set. So if we took this data set and arranged it in numerical order, which down here, you can see that I've arranged it in a nice numerical order in this chart. The median of this data set is 19.8. So that's the middle value, or the median value. And the median value for the random mall shoppers is 28.6. The mean is just another word for average, which is the more common word for it. So that means that to get the mean, we're going to add up all of the numbers in this data set and then divide it by the number of entries. So we would add up all these and divide it by 1, 2, 3, 4, 5, 6, 7, 8, 9, which you can see Excel has already done nicely for us, because if you just type in equal average and you put the range of your data set, Excel will give you the number for you. It'll do the same thing for median. If you just type in median and give it the range of the data set, it will give you the median yourself. So you can see over here, the same things have been done. Now, the standard deviation, we will talk a little more about later, but you can see here that the standard deviation in this first data set is 3.45. For simplicity's sake, let's call that 3.5. So the standard deviation for this data set is 3.5. That means that for, here's my nice pretty bell curve. So that means that for each standard deviation, which is each one of these sections of the bell curve, that should take up 3.5 spaces along this x-axis. And as you can see, the standard deviation, that median value we know is 19.8. So 19.8 should be the very top of this bell curve, and we can see that it's roughly at 19.8, and that it extends to roughly 23.5. So that would be just about right for what the standard deviation is. So each one of these is the standard deviation. And the really cool thing is that for every set of data that doesn't have outliers in it, which we'll get to what outliers are later, that the standard deviation will always break down the same way across your bell curve, that your first standard deviation here should be 68.2%, and then your next standard deviation will be 13.6% on either side, for a total of, let's see, quick math, 27.2. And then the outside ones would be 4.2%. And each one of those is one single standard deviation. And the coefficient of variation here is 0.171. We find the coefficient of variation by dividing our standard deviation by our mean. That means we want to find, as you can see here, that's Q6, which is this cell right here divided by Q5. So 3.459 divided by the mean gives us this coefficient of variation, which is how much the standard deviation will vary. And you can see all the numbers here for the random mall shoppers are much larger than the numbers for the Army recruits, which makes sense because Army recruits are most likely in better physical condition than just an average random shopper, which means their BMIs are probably going to be lower, which is represented because if you look at the chart down here, we have a couple of numbers that are considerably high. This is the 45.7, and all the way up here, this is the 72.5. So the median, the middle value of this data set is 28.6, but the mean, so the average of this data set is 33.5, which is 13 whole points bigger than the average Army recruit BMI. We can also see the standard deviation is absolutely massive. That's because we have these outliers here which are throwing it off. They are so far out of line with the rest of the data that it's throwing the standard deviation off. A proper standard deviation can't be calculated for this set because these are so far off. And if you see, when we go down to this box and whiskers graph here for the random mall shoppers, this is where most of the data is going to fall. These lines here are the standard deviation from the median. So you can see the median, because we know coming up here, the median is 28.6. So the middle of this should be at about 28.6. And it looks like it is about at 28.6 because this line here is the median. That looks to me about 28.6. And we know that the standard deviation is 17. So if we go 17 off the off of 28.6, then it will extend down to these bars. You can see that the 72.5 entry is way outside of this standard deviation because it's an outlier and it's throwing off this standard deviation a lot. And if we were to calculate the standard deviation of a data set without the 72.5, it would be much smaller. In fact, why don't we do that real quick? Because it's quite easy to calculate standard deviation in Excel. So let's pretend that this 72.5 is a more normal number. Let's turn it into 25.6. I know that's kind of around a lot of these others. And since we set up our formula property in Excel, I won't even have to do any additional math. It'll change it on all these numbers on the fly for me as soon as I hit enter, which I just did. And you can see that the standard deviation shot down to 8.9. And if we go down to this box and whiskers, the box and whiskers chart won't update on the fly. But if I created a new box and whiskers chart, then this dot wouldn't be up here anymore, and it would fall more within a standard range. And if it fell within a standard range and a standard deviation, then we would be able to form a bell curve with this data. Because with the outlier, we're not able to form a bell curve because this outlier is throwing it off, and it would be unreliable data. And as discussed in scenario 2, we don't want to misrepresent data. We don't want to mislead people. So you can see that the mean changed, the mean dropped considerably, the median changed a little, the range changed considerably. It actually even got smaller than the Army recruits range. And the biggest change was in the standard deviation and the coefficient of variation. So I'm going to go ahead and turn that back to the number it was before. And we can take a greater look at this data down here in our bars and whiskers charts. So as we talked about up here, the median of the Army recruits data was 19.8. Now, if we go one standard deviation up, which if you'll remember is about 3.5, we should get these next two, once they are averaged together to give us our Q3 value, which is what we did. We added these two cells together and divided by 2. This number here should be roughly the median plus 1 standard deviation. If it is a standardly, normally distributed set of data, then the Q3 and Q1 should be within 1 standard deviation of the median, which is the Q2. But it's more commonly referred to as a median. So if we take a look and we're saying the standard deviation is 3.5, well, if we add 3.5 to 19.8, we do get close-ish to 22.85. Once again, I'm rounding this number. So this, in reality, is a standard deviation away, or pretty close to standard deviation away from the median. And this one, as you can see, is it's not quite as close as the Q3 was, but it's still pretty close to a standard deviation. It's close enough that this is still a normally distributed set of data, but you can see it's a little smaller than a standard deviation should be. But if we go down here to our pretty little bell curve, we can see that for the man, this really is an old copy of this document because all my Axis titles aren't here either. Oh well. So this chart is representing the Army recruits BMIs. And this axis here is each one of the individual BMIs. And this y-axis here with the bell curve, it's a little bit different to how most of these y-axes would normally be represented. What is more important to pay attention to in the bell curve is where these values fall within the range. So if we're saying so we're saying the median's here. Within one standard deviation on either side, there should be a 68.2% chance for any random data entry to fall within that range. So we can see that range extends to from roughly 16.5 to roughly 23.5. So that means if we took a random number, a random data entry, it should fall within this range here 68.2% of the time. Then it should fall within either the second standard deviation on either side of the median 27.2% of the time. So either in this chunk here or this chunk here, or if you want to look at it individually, there's a 13.6% chance that a random data entry would fall within just this section, and it's 13.6% chance that would fall within just this section. Then here, for these two, I accidentally just moved that a bit. These two each have a 2.1% chance to have a data entry fall within them. So together, for the third standard deviation, there's a 4.2% chance. And then normally, that's what most bell curves go out to. You can go out to a fourth standard deviation, which in this chart here we have, but there's such a small percentage chance that anything would fall within that we didn't include it in this bell curve up here. And over here, this is a table of the percent chances that each one of these data entries here could come up. So we know the median for this set, if we scroll back up and check again, remember, is 19.8. So if we look for 19.8, the closest one that we have to 19.8 is 20.3. That is the most likely chance. If we move our decimal place 2 places over, we would, as you do for percentages, we would have 11.5% chance that a data entry is roughly around this number, 20.3, not necessarily that number exactly, but around there. Because we know for this whole standard deviation, if we added the percent chance for each one of these little points on the graph, it would come to 68.2. And as you can see on this table here, we actually went out to these fourth standard deviations, and these numbers are so small that they're actually currently being represented in scientific notation. That's how small of a chance that there is for the data, for a random data entry to fall within or near those ranges. And once again, the reason why we were unable to make a nice bell curve for the second set of data is because we had this one really big outlier that made it so that this data set was not standardly distributed. Otherwise, we could have made a bell curve for this guy too. And I believe we've discussed everything that we need to discuss here. So let's go ahead. Let's move on to talk about investment, sales, and profits. So for this, we were looking at a variety of different ways to calculate profits and investments. In the company that we used for this exercise was Elon Musk's Boring Company, which were selling flamethrowers to be able to fund other ventures of his. So this is a really quick demonstration of an extremely oversimplified profit chart. So we can see the formula we're using for this chart here is profit equals 500 times X, where X is the number of sales. So this is a very, very simple way to look at profits. The more sales you get, the more money you will have, which makes sense. But there's a lot more that goes into running a business than just selling things. So the real formula for profit is not that nice and pretty, but we'll get into that later. Or no, we'll get into that now. We'll talk about the profits first, and then we'll talk about interest. So a more accurate representation of how profits really work in business is this formula here, which is 6.212 times x squared minus 1200 times x minus 12,000. So as you can see, our initial investment into this venture here is $12,000, which is the last number here, which will be our y-intercept, because that is showing how far down we start on the y-axis. If that, for instance, was plus $12,000, we would have started at a positive $12,000 on the y-axis. But we didn't. We initially invested $12,000 into the company, and then the two terms here that have X within them is showing how much money we'll make compared to the number of sales that we have. So initially we invested here, and as you can see, for quite a bit of time, even though we were selling more and more units, we were actually losing money. And that's because businesses have a certain cost to running them, which takes time to be able to become profitable, because it's not just our initial investment, but we also have to pay our employees and upkeep, and we have to manufacture all the goods that we're selling. So it takes us quite a while before we actually stop losing money. So you can see right where this red is circled, and this is approximately our greatest possible loss here. It's not actually, because we're only representing these X values by 20s. So it's not, it didn't perfectly fall in the 20, but it's pretty close. You can see that we were at about negative $70,000 in the hole before we stopped losing money. And then we started to recover. Now we still haven't made it to be profitable. We still haven't overall made money on the business. But once we pass the vertex of this graph here, we are starting to make money back. We are, instead of losing money, we are starting to gain money, but we still haven't quite made a profit yet. It's not until we reach a little over 200 units sold that we break even. So we have made as much money as we have lost, because keep in mind, throughout this entire time, we were losing all of this money, and it wasn't until we sold about 200 units that we broke even and were no longer losing money. And then we wanted to know how many sales it would take to earn $90,000 in profits. So not just breaking even, but how much money, or how many units would we need to break to break that threshold of $90,000 made in profits. So we calculated that to be at about 260. It's a little less than 260, but once again, we're only working in increments of 20 here, so I couldn't represent what it was exactly. So now we're going to take that knowledge that we've learned about profits and about how businesses function with an initial investment, and then losing money with operational costs until they're able to sell the product or service long enough to break even and eventually make profits. We are going to take a look at some investment examples here. So just like the profit, where we started off with a simple formula and then used a more complicated formula, for investments, we're going to start off with a simple investment formula, which is that your overall money, which is your total amount of money, is equal to the principal amount you invested. So that was the initial invested amount. So in this example, the principal would have been the negative 12,000 right here that we invested. So your total amount of money with simple investment is equal to your principal times 1 plus the annual interest rate. For this example, we used an interest rate of 6%, times the number of years. So this is assuming that it is being compounded annually, which is how simple interest is compounded. So you can see here in our formula that we are taking this cell here, which is the principal. We are then, and we put the dollar signs around it to lock it in, because our principal for all this is always going to be the same, because that's how much money we put in regardless. Then we, in our parentheses here, we said 1 plus the annual percentage rate. We also locked that in because that's not changing, times the amount of time that it's been, which is this cell, this cell right here. And the really handy thing about Excel is if you set up your formulas like that, then it'll automatically do all the work for you if you just drag it down. So you can see going down the list, all of this is the interest being compounded over time. But you can see this grows at a pretty slow rate. If we go down here to this chart, this is a linear rate of progression, because we're not bringing anything to the power of anything. We're not having exponential growth. It's a linear growth because it's only adding things together and then multiplying them. We're not raising anything to the power of anything else. So it's a simple linear function, and it will continue like this forever. But if you're an investor, you don't want this simple linear growth, because you can see it pretty quickly gets outpaced by these ones that are growing exponentially. Because with the exponential growth, either if it's being compounded yearly or being continuously compounded, they grow faster because the total amount is being constantly reevaluated. And you can see our formula here, match the formula up here. We plugged it in much in the same way. And with these yearly compounding interests and continuous compounding interests, you can see they're about the same as each other. The continuous compounding rate is a little better. If these numbers were much larger, say for instance, I'm going to real quick change our total principal. Instead of being 5,000, let's change it to 500,000 and see how that changes things. So you can see these are all about the same function. It's not a massive difference between the way that these looked last time. This linear one will have the same slope because nothing about this changed. It's just bigger numbers. These guys will actually have about the same rate of change, but you can see the difference between them has gotten bigger, but it's not much bigger. So the continuously compounding interest is better than the interest that compounds yearly, but there's not a ton of difference between the two. So let me change everything back to our nice smaller numbers. So if you are an investor investing your own money, you really want either yearly compounding interest, or best case scenario would be continuous compounding interest. But if you were unable to get continuous, yearly is still pretty good. There's not going to be too much of a difference between yearly compounding and continuous compounding, as you can see. But if you're on the other side of that and you were a business owner looking for investors, you would, if you could afford to, you would want to offer your investors only simple interest, because they end up getting less of your money over time as compared to the yearly compounding and the continuous compounding. So if you just needed, if you didn't care about how many investors you got and you were just opening up for investors just to do it, you might just offer simple interest instead of yearly compounding or continuous compounding. But if you needed investors really quickly in the short term, say for instance, go back to our example, the company here is deep in the red and they're about to run out of money. Maybe they need investors really soon. In that case, you might offer your investors a continuous compounding or a yearly compounding interest style, and you might even offer a greater annual interest rate than 6.0%, because the larger you make this interest rate, the more money investors will make, which isn't the best for you as a business owner. But if you need capital immediately, then you want to make it attractive for investors so that they will give you the money that you need And in order to make it attractive for investors, you would want to either give them yearly compounding, continuous compounding interest, or give them a higher annual interest rate so that they would be more incentivized to invest in your company. I think we've talked about everything we need to talk about here, so let's move on to the final scenario. So this scenario here is a more personal scenario than the last ones have been. The last ones have been just general mathematic principles and ideas. This one is still the same, but it's more talking about our personal 5-year financial plans. So as I said earlier, my major is social work, and I'm going to school to become a licensed clinical social worker. And you can see over here that the median salary in the US for a licensed clinical social worker, which requires a master's degree to get, and then 4,000 supervisory hours after your master's degree before you can get your LCSW. So it takes quite a bit of time. In fact, with this 5-year financial plan, in 5 years, I won't technically have my LCSW yet. Within 5 years, I should have my master's of social work, but it will take me 2 further years after I get my master's of social work to get my LCSW. But for simplicity's sake, so I didn't have to change the 5-year plan, I just fudged it a bit and said that I would have my LCSW in 5 years. I won't have my LCSW in 5 years, but the rest of these principles will still remain the same, and we can still evaluate them properly. I'm just noting I won't actually have my LCSW in 5 years. So you can see the median salary in the United States for LCSWs is $64,600. This is also right about the same median salary as it is in Arkansas for an LCSW. You can see the total range here. The lowest would be paid $47,000, and the highest reported, at least, is paid $87,000. For the purposes of this 5-year financial plan, I use the 47,000 number for a few different reasons. One, in a financial plan, when you're budgeting, it's good to be a little pessimistic, not super pessimistic. If you're super pessimistic, then your numbers are going to be way too off from your actual numbers, and they won't be useful as a representation. But if you're a little pessimistic and say, I'm going to make a little less than I probably will make, like, for instance, when I enter the workforce, I will probably, when I get my LCSW, I will probably be making more than $47,000 a year for my salary. But if I just say this is the lowest amount possible, and I budget and plan around having the lowest amount possible, then any extra money I have is a nice bonus instead of the opposite, which is I was counting on getting more money than I ended up getting and had to change my budget around. So for the rest of this, we will be using the $47,000 figure. I also use that because once I do get my LCSW, I would be on the lower end of experience. So typically, the less experience you have, the less money you will make, typically. So we can see here, this is my gross income. I just made it a flat, nice, even 47,000. For the purposes of this, I didn't include any of the other rest of these numbers. It gets a little more complicated. There would be, I would be making investments, I would be making interests, and I may or may not have a spouse's salary contributing to this overall household income. But for simplicity, we're just going to use this $47,000 as the gross income. And then in order to make your budget, you want to find your gross income. So the total amount of money that you are making. This is a monthly budget. So this is $47,000 a year, but we want to find the total monthly income. So if I was making $47,000 a year, the monthly income would be $3,917. And then we want to find the monthly expenses and make sure that for everything that I'm paying for each month, that I'm making enough money to pay for everything. So we're going through internet and phone. I pay about $120 for my internet and phone together. Groceries, I like to cook. So even though I'm just a single person, I spend A little more on groceries than probably an average single person does. So 300. So my groceries are a little higher. Mortgage, we used a sample example house here. This is the type of house that I would like. It's a nice, small, secluded property, not too close to a city. And we used an online mortgage calculator to determine that the monthly mortgage payment for a house of this type would be about $580. Credit cards, this is like just a general catch-all category towards like credit card payments. I put it in at roughly 100. It wouldn't necessarily be that. For instance, when you're spending money on groceries, you may want to pay for those on a credit card and then completely pay that off at the end of the month to help build your credit. So this number here is a little more representative of maybe the amount of credit that you're paying, but not completely paying off, because you may want to pay for groceries on a credit card and then completely pay that off by the end of the month to help your credit. Fuel, I would be spending roughly $42 a month on fuel. And now for people who own a car, like I myself own a car now, and I definitely spend more than that on fuel in a month. So you may be wondering, why is that so cheap? Well, the type of car that I'm interested in purchasing is actually an electric car that has roughly an annual fuel cost of $500, which means that's about $42 per month. So I would be spending a little more, a $30,000 car. I mean, that's not outrageously expensive, but it's a little more than like the cheapest option of car available. But in the long run, it'll save me money on gas. So I'm spending less money on gas. This number is a very rough number. We'll say we're contributing $100 a month to an IRA. Ideally, I would be contributing more money to that than $100 a month, but this is a very rough estimate. So for instance, if my income was more than $47,000, a lot of that additional money would probably be going to this category here, an IRA, because I believe you can contribute $6,000 a year to a Roth IRA, and you really want to be contributing as much money as possible to Roth IRAs because they are excellent, secure, long-term investments. So ideally, that number would be higher. We're saying insurance for car and home would cost roughly $250, which is about accurate, and maybe a little less than it should be, but it's about accurate. Then we calculated how much the car loan for this car up here would be, which was $553. Utilities, about $150 a month. That's about how much I pay for utilities now, roughly. Clothing, I very rarely buy clothing, so I just put it as a 25. That might not be completely accurate, but it's a rough estimation. $150 on entertainment. I don't spend a lot of money on entertainment. I can generally entertain myself pretty cheap. What's not cheap for me is the medical and dental category. I have several health problems, so I end up spending quite a bit of money on medical expenses each month. This is actually, I wanted everything to be a more simplistic example for this, so it wouldn't get too complicated, but I probably spend more than $500 a month on medical expenses. And that's all right, because some of these I kind of overestimated anyway, so it all roughly evens out. So then we're saying maybe spending $100 a month on average for regular maintenance of car and home, $100 in just emergency saving funds, and then the taxes, because remember, we only took the gross income, we didn't take the net income. The taxes for the tax bracket that I would end up in would end up costing $815 a month in taxes, for a grand total of $3,888 of total expenses per month. So if we come down here and we break down the monthly income, which remember is this cell divided by 12, the monthly income, and then we subtract the monthly expenses from that monthly income, we're left over with a difference of $31. That means that there's $31 extra that I could allocate to any of these different expenses, most likely either to savings or the IRA. Here is a pie chart of that monthly budget with everything broken down with both percentages and dollar amounts. So you can see the biggest slices are taxes, which is the biggest one. Then the mortgage and the car are both pretty big, and then dental is the next biggest, or medical and dental is the next biggest. And then here's a 3D bar graph. It's representing the same information. So here is actually the tax breakdown for that, which is how I got to this figure here. Where's the figure? There it is, $815 a month. So if we look here, the federal marginal tax rate for the tax margin, the tax bracket that I fell within, which pretty much this entire range of data would fall within that tax bracket. So no matter how much money I made on this, I would probably remain within the same tax bracket. So the federal marginal tax rate is 12%, but the effective tax rate is only 8.53%. And that's because tax brackets don't work in the way that you would initially expect them. Say if you make over $40,000, for example, maybe anything over $40,000 is taxed at a 12% rate here. But say anything below 20% is only taxed at an 8% rate. Well, all that money, or sorry, anything below $20,000 is taxed at an 8% rate. Well, all that money that you made up to that $20,000 tax bracket would be taxed at that tax bracket's tax rate. So that 20,000 would be taxed at the 8%, and then the additional 20,000 would be taxed at the next tax bracket, which would be 12%, which is why the effective tax rate has taken that into account, and why the effective tax rate is lower than the federal tax rate. It's because not all of my money is being taxed at the same rate, because no matter how much money you have, if you make more money, you won't end up paying more in taxes. There is a myth that is often repeated that if you get a raise and are brought up into the next tax bracket, that you will somehow end up making less net income, which is not true. Only the amount of money that is being made above that next tax bracket is taxed at that rate. So that's why the effective tax rate is different there. And the same thing goes for state, although it's a smaller difference. So you can see that the total amount of income tax for the effective tax rate between the federal, FICA, and state is 20.81%, which is $9,782 in a year. So that means that the net income in a year is $37,218, which that divided by 12 will give us, or should give us, what our net monthly income is. And this number here, 9,782 divided by 12, should give us that figure right here, 815. So let's just double check ourselves and see if that is true. So I said 9,700 and I forgot 82, $9,782 divided by 12, and we hit enter, and then boom, it's $815. And I didn't include any cents for this just for simplicity, but it's actually $815.17. So that is how I calculated my tax rate. This helpful income tax breakdown is available online. If you just Google income tax breakdown or income tax calculator, you will be able to find either this one or something quite similar to this one that will help you determine the effective tax rate, which can be tricky to determine by hand. So we covered the budget. Now let's talk a little bit about time, because time management is super important for long-term success. We did a weekly time schedule. We said I said I was going to be sleeping about 42 hours a week, because on average I sleep about 6 hours a night. So 6 times 7 is 42. We're going to say working 45. This is a rough estimate. The average social worker works about 40 hours a week, but depending on the job and the position, many social workers might be on call during their off hours, or they oftentimes bring their bring their work home with them. So it's a little hard to come up with an average amount of time spent a week for a social worker, because it's not super cut and dry. So I just went with a rough estimation of 45 hours. I said about 10 hours travel time between commuting from work to commuting to other various places, about 10 hours a week just traveling. 14 hours a week for cooking and meal time, so that's about 2 hours a day roughly, which is about how much time I spend. It's maybe a little under. Maybe I would need to bump that up a bit, but it's pretty close. I am a very creative person. I'm working on a lot of like side art projects in my free time, so I give myself about 10 hours a week to work on creative projects, because a lack of creative fulfillment makes me less effective in general. I said about 14 hours a week socializing. You know, that's about 2 hours a day of socializing with friends or family. About 5 hours of exercise a week. I have 5 hours of physical therapy every single week because of my health conditions. So that is a very consistent number. 8 hours a week of just general entertainment. This volunteering section is another one that I volunteer more than 10 hours a week, but I was just trying to give rough estimations. Social workers typically volunteer quite a bit, and I do a lot of volunteer work now. I volunteer with the Central Arkansas Harm Reduction Project, and I do more than 10 hours a week of work with them currently. Then I just said general chores and errands, about 5 hours, and then just a miscellaneous category for anything that might not fit neatly into one of these for another 5 hours, which gives us a total of 168 hours, which is the amount of hours in a week. And you can see this nice, lovely breakdown of the pie chart here for how much time, the percentage of my time each week that I would spend. You know, all this stuff here is about the same, and the two big chunks are working and sleeping. That takes up more than half of the chart. Then here, I just I put together a few slides to talk a little bit about the field of social work, because I feel a lot of people may not know too much about the field of social work. It's a pretty broad name. It's not very specific. The first thing that a lot of people would probably think of for social workers might be child protective services workers, which those are a type of social worker, but there's a ton of different types of social workers. It's a very versatile degree. At its core, social work combines psychology, so the scientific study of the mind, sociology, which is the scientific study of society and social interactions and social development, and counseling, which is helping people understand the psychology and sociology elements in their world and help them be able to meet and deal with their emotional needs. And at the core, this is what social work is about, is combining knowledge of psychology and sociology to work with patients and clients to help meet their emotional needs. So this picture here, it's a kind of nice general overview. Median salary of $49,000, which is pretty close to, actually, it's a bit lower than the median salary here. This image is probably an older image, so we don't necessarily need to pay as much attention to that median salary. But this is a brief overview of things that social workers do. So they assess clients' situations to determine their needs and goals. They oftentimes have a strong desire to help others, which is certainly true in my case. They refer the correct treatment centers to clients. So if someone needs to see a neurologist or a sleep psychologist or a psychiatrist for prescriptions, social workers will be able to refer their clients to the proper resources. And they have A lot of active training is needed to meet all their certification standards. Like I said, they need 4,000 hours of supervised work after they get their master's degree to become a licensed clinical social worker. And then after that, every 2 years, they have to renew their license. And in order to renew their license, they need 48 hours of continuous education credits. So social workers are constantly attending new seminars and new classes to be able to keep up to date with the field and to make sure that they're able to provide the best help to every single client that they can. So here's a few examples of various places that social workers work. They oftentimes work in schools. They might be counselors at a school. Like I mentioned, they work in child protection agencies. They oftentimes work in correctional institutions for mental rehabilitation. They work in health and community centers for outreach. They also often work in hospitals and mental health facilities like rehab clinics. They can have their own private practices that would more often be counseling practices in nature. They have family service agencies. Another one mentioned here are adult protective services, just like child protective services. And they work with government agencies a lot too. And you can see 60% of mental health professionals are clinically trained social workers. So social workers make up the majority of the mental health field. They're kind of like the boots on the ground version of psychologists. They work more with clients directly, and they will often refer clients to psychologists or psychiatrists if they need a more specific viewpoint on certain issues. So here's some more information about medical social work, which is the area that I'm looking to get into. Medical social workers help patients, and the patient and their family is the social worker's top priority. Their responsibilities and duties can change a lot from person to person. Social workers are their clients' primary advocates. They can help them through difficult times. They can help them physically, financially, emotionally, and mentally. Social workers serve as guides and compassionate listeners to help their clients best meet their emotional needs. The reason why I'm getting into social work specifically is to help combat the opioid epidemic in this country, which is an awful epidemic that is plaguing this country, especially young people in this country. In the 18 years that this data is looking at, from 1999 to 2017, almost 400,000 people died from an opioid overdose. The 1990s saw a marked rise in prescription overdose deaths. In 2010, there has been a massive rise in heroin-related overdose death. And in 2013, it is when the massive rise in synthetic opioids came about, which is substances such as fentanyl and tramadol combined with other things that can be very powerful. The last thing that we're going to be looking at today is some nutrition info. So I have been vegan for 3 years for ethical reasons, but also for health reasons. It was recommended to me by my dietitian. And this is also about the diet that was recommended to me. So this is the average number of servings for each one of these categories of foods per day. So in my diet, I'm aiming to get somewhere between 1,800 and 2,200 calories. If I got 1,800 calories a day, I would lose weight at a healthy pace. And if I got 2,200 calories per day, I would maintain my current weight. So somewhere in between there is what I'm shooting for. And to get there, I eat about 6 servings per day of grains, 5 per day of vegetables, 4 per day of fruits, 3 per day of legumes like cashews or legumes, like peanuts. Sorry, my mind is blinking. There's a really big one. I can't forget, but there's a lot of legumes. A lot of them are like beans and legumes. Is kind of what this category covers. A lot of protein comes from there. Then 2 servings per day of nuts and sweets, and then on average about a half serving per day of sweets. I don't typically eat that much sweets. So this is a pie chart that breaks down the percentage of each one of those categories and how much I eat per day. I have a variety of different information about veganism. Here, if you're interested in learning more, youaretheirvoice.com is an excellent resource for all things about veganism. And here's a lovely infographic that kind of represents the same information that I presented above. So the grains, you want 6+ servings a day on average. Servings about half a cup, so you want around like 3 cups of grains. So grains include things like brown rice, quinoa, millet, wheat berries, typically focusing a little less on the more carbohydrate-rich stuff like bread, more on like the rice and the quinoa and the millet. Vegetables, once again, a serving is a half cup cooked or a cup raw. Really, especially focusing on leafy greens and cruciferous vegetables because they're super nutritionally dense. They have a ton of really good vitamins in them. Fruit, we want about 4 servings of that per day. Legumes, about 3 servings of that. This category is including beans and lentils, that was what I was trying to remember earlier, and like hummus and tofu and soy milk. There's a bunch of things that fit into legumes, and a lot of protein comes from this. And nuts and seeds, you don't want too many of them, but the ones to really focus on are flax seeds and chia seeds for a reason that I'll talk about in just a second. Because over here, we have all of the nutrients required to have a healthy diet, and these are all examples of how you can get all of these nutrients in a day. So calcium, here's a long list of a variety of different things that you can get calcium from. The daily recommended intake is about 1,000 milligrams, so a gram of calcium a day. I eat all this stuff, but I'm also naturally calcium deficient because of my health issues. So I also supplement calcium as well by the recommendation of my doctor. Iron, the daily recommended intake of iron for men is about 8 milligrams. So getting 8 milligrams of iron, especially through all the leafy greens and the legumes like lentils and beans and stuff, is quite easy to do. Protein is also pretty easy to do. So for protein, you want 0.8 grams per kilogram of body weight. It's very easy to get protein. I've never had an issue getting protein. Zinc, you want 11 milligrams per day for men. Once again, very rarely an issue getting zinc. A lot of these things overlap with each other. The big 3 issues for vitamin deficiency for veganism, this is the only negative, or not negative, this is the only concerning part of a vegan diet. Everything else is very healthy. All the World Health Organizations are in consensus that a properly maintained vegan diet is one of the healthiest diets that you could be on, but you really need to watch out for these 3 key things. The first thing is omega-3 fatty acids. The most common source for omega-3 fatty acids for people is in seafood, but vegans don't eat seafood, so they need to find their omega-3 fatty acids from another source. Ideally, you don't want to take omega-3 fatty acids as a supplement if you can avoid it. Generally, you don't want to take, generally you want all your nutrients to come from whole foods as much as you can and not have to supplement as much, which is why the flax seeds and the chia seeds that I mentioned earlier are so important, because 1 teaspoon of flax seeds and chia seeds can give you 500 or 600 milligrams of omega-3 fatty acids, and the recommended intake for men is about 1.6 grams. So if I have 3 teaspoons of flax seeds a day, or 3 teaspoons of chia seeds a day, or 3 teaspoons of hemp seeds a day, or 1.5 ounces of walnuts a day, I will get my daily recommended intake of omega-3 fatty acids and not have to supplement, which is good. The next thing to really watch out for is vitamin B12. Vitamin B12 is most commonly found in meat, more specifically in the things that animals eat. especially animals like cows. Now, in today's age of industrial farming, more and more people, including omnivores, are vitamin B12 deficient because there's less and less vitamin B12 to be found in factory farmed meat. So it's actually recommended for everyone to make sure that their vitamin B12 levels are good and in check, and to supplement if needed. Because of my health conditions, I already have a naturally lower amount of B12, so I do have to supplement with B12. Unfortunately, there are not good ways of getting B12 in whole foods. Leafy greens do have some B12 in them sometimes, but it's a negligible amount. If you are going to transition to a vegan diet, you really should supplement your B12. But a lot of people need to supplement their B12. And even if you're not interested in switching to a vegan diet, I would highly recommend to check with your doctor to make sure that you yourself do not need to supplement your B12. Then we also have vitamin D. I'm also naturally deficient in vitamin D, and the vegan diet has a little less vitamin D than the standard American diet does. So it's also recommended to take a daily supplement of vitamin D, which I already have to take anyway. So that doesn't really affect me that much. And I believe, yes, we have covered everything. I want to thank everyone so much for sticking through to the end with me and for watching my Excel report. Like I said, if anybody watching this has any reason that they might want to get in touch with me, they can get in touch with me through any of these means. I am available pretty regularly. I have flexible hours. So thank you very much for watching. Have a good one.